Hello again. The next presentation is named Security Data Innovation in HealthTech Organization. And Michael is a distinguished engineer for cybersecurity and digital innovation at Resilience, one of the fastest growing biopharma technology companies. He's also senior technical advisor at the University of Miami Data Science Institute and the Center for Accelerated Real-Time Analytics. He has more than 20 years of experience solving complex cybersecurity and technology challenges and holds 14 cyber and blockchain patents and has led cybersecurity products and cybersecurity for industry, government, and academia. So welcome, Michael.
It's great to be back. Can you hear me all right?
Yeah, we hear you.
All right,
very
now
well.
Can you see me or can you just see the presentation?
We see you at this point, and now we see both you and presentation.
All right. Well, hopefully the presentation looks better than me. It's been a long week, and it's only Thursday, but it's great to be back, and thanks for your hard work making this happen. Okay, with no further ado, I guess that's a start. I was just cut off there. But again, Michael Mylrea, today I am going to present on secure data innovation in the health sector with a focus on biopharma manufacturing. So what have we seen in the last 2 years? What have we seen in the last 30 years? What have we seen in the last 100 years? Before we look forward at some of the disruptive innovation, it's important to look back, and it's important to level set and calibrate where we are today. So in the last 100 years, there has been a major change in how drugs are manufactured, and the sense that we've converged our cyber physical systems, our information technology and operational technology. We've automated, we've leveraged robotics. A number of previous panels talked about some of the disruptive potential around machine learning, as well as the limitations to take these large, prestigious data sets and basically illuminate and highlight patterns and intelligence and insights from these large data sets. Now, at a recent panel I was on, someone likened this phenomenon around data as data being the new oil. And in debate and in conversation, we started to just pull the thread on that a little bit. Data is the new oil. There's a lot of analogies there that I think are similar, but in many ways, as one of the other panelists had made the point of, it's a lot more like water, that there's plenty of data out there, but it needs to be refined. It needs to be prepped before it has value for distribution. And then I'd also argue that 75%, 80% of the world's surface is covered by water, but most of that's not potable. Most of that water can't be consumed. And the same thing we're seeing in the health tech space and other critical sectors, that there's plenty of data out there. The challenge is, how do we transform that data in our organizations to glean insight and intelligence from that data? What we saw in the last 2 years, in many ways, was unprecedented, and that we saw during the pandemic. All organizations became health organizations, and that in absence of a health ecosystem that was functioning, we saw critical ports and transportation ground to a halt. Hospitals and essential services overwhelmed, critical supply chains and manufacturers disrupted. And while researchers worked to develop a vaccine, we saw a new threat, a nonlinear evolving bio threat combined with a cyber threat. This is new. And during this fog of war, while a lot of different allies and even previous opponents came together to find a cure, others decided that this was an opportunity to weaken opponents. So this was a time in the last 2 years we've seen an increasing number of nation state-backed adversaries, well-funded criminal gangs take advantage of this situation to target everything from R&D to develop new vaccine to the critical manufacturing needed to get a vaccine out to the masses. And so we're seeing not only an evolution of this tactic, but if you look at the tactics, techniques, and procedures, the sophistication, the frequency, the severity of these attacks really require this entire space to move beyond cybersecurity. So our traditional defenses and paradigms we use to keep cyber adversaries out of our networks and systems are broken. They don't work. And part of that is because of the digital transformation. So you see an opportunity on one hand, and then you see a major challenge on the other. For us to unlock these opportunities, we really need to solve to that grand challenge around how do we secure our data. So that's the journey I'm going to take you on the next 25 minutes. I'm going to discuss some of the innovative solutions we're working on, as well as some of the challenges, starting out, of course, with the challenges. I've been working in this space for about 2 decades, primarily focused on cybersecurity for industrial control systems and operational technology. And then on the innovation side, I've been involved in a lot of applied machine learning, digital twin, and blockchain work. When we look closer at this space, again, we see this incredible opportunity to transform a sector that in many ways, well, it's transformed, it's going through digital transformation. If you look at bioreactors, if you look at the technology, if you look at a lot of the processes, there's still a lot of things that if we look back and, years ago when penicillin was developed and manufactured, there's still a lot of similarities, and this entire space is truly ripe for disruption. Now that's if, and I have prefaced that with, that's if we overcome some of these challenges. So what did we see during the pandemic? As users, as people working in critical, control system engineers, automation engineers working in this space, working in biopharma manufacturing, left and went home and started operating these critical systems remotely, that attack surface that was originally part of the transformation. So that's the connection of our cyber and physical systems, our industrial control systems, and our information technology. That's unlocked incredible opportunity as we see, but it's also widened the attack surface. And it's important to preface it with a lot of these systems were never designed to be connected to the internet. So they lack basic encryption and authentication. They'll communicate batch recipes and passwords in plain text. And so if there's any infiltration, that data can be exfiltrated, it can be manipulated, it can be denied. And so that's part of the challenge with all this is when we look at digital data, again, it's easy to manipulate. And so the ability to trust, the ability to have integrity of data also is absolutely imperative to have integrity and quality of product. And so there's absolutely no jeopardizing that at all, because at the end of the day, we're producing drugs that people put in their body. And so security is absolutely always a top priority. But here we see during the pandemic, this attack surface significantly expanded as control system engineers and automation engineers started working remotely. These systems, again, never designed to be connected to the internet, became increasingly vulnerable, and you saw an increase in frequency and severity of attacks targeting these systems. Beyond manufacturing, beyond the supply chain, at the patient level, you see that cyber attacks go through our entire health ecosystem, our entire value chain. And again, the frequency, severity of attacks are increasing exponentially. And we're actually seeing new trends here that I'm going to get into. One of the challenges when we look at threat intelligence from data breaches, which is important, right? You need to understand the offense or threat if you want to defend against it. But when we look closer at it, this is only what's being reported. I think I oftentimes question the percentages and the models around some of the threat intelligence data we see. Other things, however, that we're looking at is, again, the sophistication. So you're seeing adversaries now that instead of using malware that's been around before where there's a signature for, so similar to a virus in the way that your immune system works, it has a signature to defend against what is known viruses that are known. Stealthy malware, zero-day exploits are very difficult to detect because they don't have a signature heuristic. They're complex, they're nonlinear, they're evolving. Not only are they polymorphic, but they're metamorphic. And so if you're using, if most of the current cyber defenses, it's very, very difficult to detect these attacks, localize and neutralize or remediate these attacks. And as a result, we're seeing that the Rubicon between a cyber attack, ones and zeros, shutting down a laptop or a router, now that we've connected our operational technology, our water, our bioreactors, all of our critical systems, we're seeing that these attacks have now really moved beyond just cyber to physical. And you're seeing sophisticated stealthy malware now become killware as things like ransomware traverse unfettered through our networks, through our systems, lock up critical machines in hospitals, shut down critical databases. And worse, you're also seeing adversaries that are trying to manipulate our cold chain. You're trying to see adversaries not only to steal IP, not only to shut down networks and systems, but to actually make stealthy manipulations to drugs to cause harm to reputation, life, and truly physical damage, kill people at the end of the day. So you've seen, again, this evolving threat that we need to evolve our defenses to also as we go through our digital transformations. And so here's just another example of a number of these attacks over the years that have gone, again, from cyber to physical and actually have create kinetic damage to systems. And when we look at them and we look at the current defenses, we quickly realize that the current defenses are not keeping up with the sophistication of these attacks. Couple reasons for that. I mentioned signature heuristics. So on an average day, you'll have about 350,000 new pieces of malware. And oftentimes the ones and zeros aren't that different. So it has a heuristic, it has a signature that our intrusion detection systems know they can detect, remediate, deny. With a lot of these, however, again, you have zero-day exploits. You have systems that, again, have default passwords and usernames. Were designed for functionality, ease of use, interoperability, cost. Cybersecurity was oftentimes an afterthought. And then finally, a lot of the solutions out there, such as vulnerability scanners, some of these legacy systems don't have the CPU, they don't have the horsepower to be scanned. And so when you use a traditional IT security tool for OT, you can crash these systems, you can degrade service. And with GMP or GXP systems in the pharma manufacturing space, you could create headaches around quality and validation. And so not only are we not keeping, is this whole space, this sector not keeping up with a cyber adversary that's evolving, a lot of the regulatory and policy requirements around this are also need to be updated to keep up with this evolving threat. So that is the challenge. Let's spend the next 10, 15 minutes discussing a little bit about the opportunity, because it's not, I don't want to present that the sky is falling, that there are no solutions to this space. What I am suggesting, however, is that a paradigm shift needs to happen. So if we traditionally invested in cybersecurity to improve the confidentiality, integrity, availability of systems, and to keep adversaries out, because we've added this connectivity, this automation, this robotics, the interoperability as part of our digital transformations, we need a new paradigm. The current paradigm is not working. And so we need to look also at the business opportunity. Traditionally, no one would ever say that cybersecurity business opportunity, you invest in cybersecurity to buy down risk, to remediate risk. It's a risk reduction exercise oftentimes. That has to change. We have to look closer at opportunities to better understand what normal looks like for these systems. What does abnormal look like? What does an anomaly look like? And how do we explain that behavior behind the anomaly? So now, instead of looking purely at the ones and zeros as we have in cybersecurity the last 2 decades, we're starting to look closer at the physics. We're starting to look closely at what normal looks like in a bioreactor from the perspective of physics, frequency, voltage, other ambient. And as we understand those physics, which are much more difficult to spoof, they can be spoofed, but much more difficult to spoof than the ones and zeros, and our TCP/IP stack and our IT stack. Once we start understanding those, we can start better understanding not only what normal looks like, but we can start collecting, prepping, and learning on these prodigious data sets to understand things like, do things like predictive maintenance, do things like reduce false positives of deviation, do things like improve efficiency and scale. And so we're doing that by creating this high fidelity, living, breathing, dynamic model that's simultaneous, that continues to update. And how do you do that? You do that through digital twin technology. Previously was a chief product officer and senior technical director at GE, which is really out in front. GE Research is really out in front on digital twin work, and we're working with to partner up with them and other leaders in this space to create these high fidelity living, breathing models. And I mentioned not only the optimization potential, so you can improve process, you can have more granular historic data, but then again, it's also important to mention the cybersecurity potential here. When you're at a workstation, there's only so many different commands and so many physical responses. And so as you start learning what normal looks like, you can establish your zone of possibilities. You can establish your boundary conditions. With those boundary conditions, you can use gradient ascent, other extreme learning methods to better understand not only what normal looks like, what's abnormal, what your degradation curve looks like. And again, you can not only understand the anomaly, you can understand the behavior behind it. So what does that mean from a cyber perspective? Let's say your intrusion detection system has never seen that signature before because it's a stealthy 0 day. Or let's say there you have an insider threat. You have someone at the workstation with deep domain expertise to cause damage. A digital twin for anomaly detection, what we're working on, has that ability to detect not only that physical anomaly, but do an inferential correlation then against the command at the packet level. And so now you're using complexity, you're using sensor actuator, cyber physical, high fidelity modeling now to not only improve predictive maintenance, scale, efficiencies, but also you have really, really high fidelity granular data on the integrity, the machine state integrity. And so you see this is really a paradigm shift in cyber physical security. And it goes back to what we originally started with. It goes back to data. And so to realize some of these goals and to understand what normal looks like, you have to look at your entire tech stack, and you have to start the very, very beginning and how you collect, you create your data lakes, and then how do you prep and how do you learn from those prodigious data sets at every layer of your technology stack. And then only with that do you really have this opportunity to make a virtual model, a high fidelity digital twin, or a virtual representation of the physical environment. And so it is a journey. The journey starts with a strategy and a problem you want to solve, and then it starts with the data. The next step really is data acquisition, collection, prep. And then you start getting into a lot of really exciting disruptive innovation around machine learning. But I've seen this also. A lot of people's digital twin journeys are oftentimes curtailed because they're looking at digital twin to solve all problems instead of having a very focused problem that they want to model around and create that dynamic, living, breathing model. You have to know right away what's the goal you want to solve. Oftentimes, digital twin is not necessarily the best decision. It's a major investment, it's resource intensive, and to do it right creates a lot of domain, it requires a lot of domain expertise. So again, digital twin, you get different definitions from different end users, but it's essentially a virtual representation that serves as a real-time digital counterpart of a physical object or process. Our focus is on the biopharma manufacturing process. And really going through it at stage one, you're collecting, aggregating, making decisions, classifying what normal looks like, what your data looks like at both the cyber and physical layers. And then you're starting to develop detection algorithms around it. A number of the previous presentations also noted some of the limitations around AI and machine learning. And so when we look closer at, especially some of these unsupervised algorithms, and we're looking at new requirements around ethical AI, privacy, as well as explainable AI. So how did your algorithm arrive at its conclusion? In biology, the biological process is highly stochastic. And so there's a ton of complexity. And so unsupervised learning and explaining how a drug was produced with unsupervised learning absolutely has limitations. And so beyond explainable AI, we're seeing other challenges around humble AI and the ability then when an algorithm gets outside of its comfortable decision boundary and is unable to provide the end user with insight, it actually notes that, it actually flags and limits that, hey, this is outside my comfort zone, if you will. The algorithm is humble and engages the human operator or notes to the human operator when additional verification is required. Now, with all this, with digital twin, with machine learning, again, we see that data is not really the new oil. It's very much like water in that it needs to be prepped. It needs to be refined in order for it to have value. The other challenge with digital data, as I mentioned, is it can be exfiltrated easily. It can be copied. It can be manipulated. And so it's difficult to trust. And so when we start looking at digital twin and federating twins across multiple sites, how do you share this granular data with your customers, with regulators, with competitors? How do you trust that that data will not be exfiltrated or manipulated or copied? There's some really exciting work underway beyond outside of Bitcoin and exciting volatile cryptocurrency transactions. The blockchain technology, the distributed ledger technology that underpins the crypto is really an exciting space where we can start looking at these prestigious data sets and better understanding the who, what, when, where of transactions, and then use a blockchain, use a distributed ledger to essentially track and trace. And this is absolutely imperative for some of these next-gen cybersecurity and confidentiality and trust and privacy goals, because as you tie your data into a blockchain, you also have this ability, for it to be privacy preserving. You can take an asymmetric hash, right, and protect the privacy as well as the integrity of the data, and then use formal methods to prove what data you have, the integrity of the data through your entire biopharma manufacturing process. When you start to unravel the technologies that underpin blockchain, you quickly realize, wait a second, I see game theory problems, I see Byzantine general problems, I see the fine cake cutting problem, Hugo Steinhaus type game theory You see self-reinforcing Nash equilibrium. So that potentially creates a number of new, exciting, disruptive opportunities, namely trust. It's the opportunity, especially in the space where you have second and third and fourth parties, and you need to protect very sensitive data and batch recipes and IP. It creates this exciting opportunity to collect, share, and use data, use formal methods to improve its integrity without risking all the downfalls and limitations of digital data, easy to exfiltrate, easy to manipulate. And so when we start looking at digital twin, when we start looking at blockchain, when we start looking at machine learning, again, well, we're talking about these as disruptive innovation. A lot of them have been around for years. And really what is going to enable disrupt, it's going to give impetus to disruption, is the novel combination of all three. And with all of that, it's going to go back to the original question that we started out with, is how do we trust? How do we secure? How do we validate and verify the integrity of data that's so easy to copy, exfiltrate, and manipulate? None of these solutions, whether it's digital twin or machine learning, blockchain, or a combination of the three, are a panacea. There are limitations in the machine learning space, explainable AI, humble AI, the lack of contextual reasoning. We're not at third wave AI yet. We have a long way to go. And then with blockchain technology in a similar way, it lacks regulation, it lacks definitions, it lacks standards. And so if you talk to 10 blockchain subject matter experts about blockchain, they're probably all talking about very different things. As part of the IEEE blockchain standards group, we have solved to a number of those issues around standardization. So we're looking, unraveling blockchain and basically looking at each layer of our tech stack to understand how it could potentially be applied. And again, there's some with all the exciting opportunities, there's still a number of cybersecurity challenges, everything from interoperability to scalability. If you have bad code, bad browsers, bad operating systems, if your code's not updated to evolve the threats, again, it's not going to be a panacea. But as we get there, we're going to increasingly see disruption in this space. We have to solve the cybersecurity challenges and privacy challenges that I noted. But eventually, I envision a place where you're at your home office, you put on your AR, VR, Oculus Rift or goggle, and you sit back and you basically have a high fidelity digital twin humming where you're able to take batch recipes, go through a process characterization, produce remotely, and then have that high fidelity living, breathing model tell you that you have machine state integrity through the entire process. And so from cyber physical convergence to cloud to manufacturing in the metaverse, this entire space is going to be going through incredible disruption in the next decade. I hope to be part of it. And I appreciate the opportunity to present some of these high level explorations I've been a part of, collaborating and leading the last number of years. Thank you for your time and attention. And for those in the States, have a great Thanksgiving. For the rest of you, stay safe. Take care.
Thank you, Michael, for a very energetic and inspiring talk and presentation. Let's see if you have any questions.
Easy ones first. No questions.
No questions. Yeah, no questions.
Well, great. Well, thanks again for your hard work making this happen. Really enjoyed the previous presentations. If there are any additional questions afterwards, please, my contact information is here. Folks can circle back. The slides can't be published, unfortunately, or presentation, but again, available to take follow-up questions around questions or even explore collaboration following the presentation. Thanks again.
Thank you, Michael.
Take care.
Have a nice Thanksgiving.
Thanks.
Bye. And this was the last presentation and the talk of this track. So yeah, for all the people who are either American or in the US, happy Thanksgiving, and have a nice day or night, depending on where you are.